Okay, welcome back to the second part of our lecture on introducing properties of solids and their types of bonding. So we've looked at molecular solids, we've looked at covalent network structures, and now we're going to look at ionic compounds and also metals. Okay, so let's think about our ionic compounds. So here's an example of one, which is sodium chloride, also known as rock salt, or if you're a geologist, you would know it as halite. It's got this beautiful cubic structure, and if you're looking at samples in a lab, it's the one that has lick marks over it. Yeah, geologists do actually lick their rocks. Anyhow, so basically you've got sodium, which is smaller, and chloride ions, which are held together by quite strong attractions, so the electrostatic attractions between oppositely charged ions. So these Coulombic interactions. Effectively, we can consider these as spheres of fixed radius, and they will basically approach each other until the point that they get to an equilibrium distance of approach, when their own electron clouds start to repel each other. I should mention that those strong electrostatic attractions between the ions lead to very strong bonding, which means that they have very high melting and boiling points. Okay, so how do we tell our ionic radii? How on earth do we know this? So what we can actually do is we can actually draw up a picture from something which is known as X-ray crystallography or X-ray diffraction, and it basically does exactly what it says on the tin. Nothing more difficult than this. So here's a source of X-rays. It fires into the crystal. The X-rays are approximately the same wavelength as the spacings between the atoms held within its crystal lattice, and this causes those X-rays to actually diffract. Okay, and the diffraction pattern that you end up with actually relates to that internal crystal structure. And so what you do is you actually build up a heat map of electrons effectively, which then you can relate to the ionic radii. I've actually whacked in some of my old data on this, which is XRD data, just so you get a sense of what it looks like and what it can be used for. This was actually wanting to determine the bulk composition of a sample. So I had a lump of mud, as you do, and I wanted, was an interesting lump of mud, I will add. And I wanted to basically know what its composition was. So this is another use you can have for XRD. And so each of these peaks relate to a mineral. So here I think we've got quartz, is quite high spike, and this is feldspar, quartz. So lots of these peaks. Oh, that looks like halite there, quartz. Was that chlorine? Anyhow, micas, basically what you might expect in a mud sample, but it just shows you that you can actually identify lots of different crystal structures within a bulk sample. And please note that XRD and XRF, X-ray fluorescence, shouldn't be muddled up. They're two very different analytical techniques. Okay, so the point of minimum electron density between the two nuclei define that limit of that ion. The electron cloud of the atom scatters those X-rays, and that degree of scattering, as we've already mentioned, is proportional to the atomic number. Okay, so we cannot analyze individual molecules, as that diffraction pattern that we get is actually far too weak. Okay, so we can, but it doesn't actually tell us that much. So if we get lots of scattering and build up a big picture, that tells us a lot more information about the size of our ions. Now, XRD is great. Okay, it is great actually. It's incredible when you think about what you're actually doing. But it provides us the first real evidence of a double helix in DNA, and has actually been really important in characterizing some very useful molecules such as antibiotics. Anyhow, back to ionic solids. We basically build up this heat map of electron density. So here is our heat map of electron density. If you imagine this builds up into our lattice structure. Now, I just want you to just keep this in mind. It's going to be important for later discussion when we think about how we predict our structures. Okay. Right, okay, so I think that's all I've got to say on our ionic compounds for now. So let's move on to something a little bit more interesting. Let's think about our metals, and as we already discussed, they have some really interesting and useful properties. Okay, let's talk about metallic bonding. So we all know that already from what we've already been taught previously that metals can really easily lose their valence electrons, and this is why we see it that if you apply a potential difference across a metal, that the electrons will flow. Okay, so as such, because they can lose these valence electrons really easily, they also have really low ionization enthalpies. I'll put my false teeth in. So effectively what we can think of is these atoms are roughly fixed in a lattice position. They're vibrating around, but they're surrounded by a delocalized sea of electrons which can randomly move wherever they want to, apart from, of course, when that potential difference is applied and then the electrons start to flow in a particular direction, forming a current. We also know that metals are malleable and ductile. We can draw them into wires if we want to. If we hit it with a hammer, we can dent metals. It's not brittle, it doesn't break. Okay, and this is because those interactions between those atoms, which allows the atoms to move past each other. Okay, so they're held together by this delocalized sea of electrons, and they're basically atoms are actually able to move. Just to say, however, this does not, our idea of what a metal is, it does not provide us with a full explanation of how metals behave, in particular why it is that conductivity varies with temperature, or why some materials are what's known as semiconductors. And to do this, to explain this, we need something else, and we need a theory called band theory. Okay, so to understand band theory, you need to cast your mind back to thinking about molecular orbitals. Okay, and we're going to use lithium here as an example. So this is our configuration for lithium. So we have 1s2 and 2s1. So we have a partially filled s orbital. So when two lithium atoms come together, both with a partially filled 2s orbitals, they will combine together to fill that bonding orbital, leaving your anti-bonding orbital empty. Okay, so our bond order ends up being 1. So basically, okay, so when you have lots of lithium atoms coming together to form a solid, you have many millions of these s orbitals which interact, and they all have very similar energies. And those they will overlap to form what's known as a valence band. Okay, so here we have our lithium atom with our partially filled s orbital. Here we have Li2, Li3, Li4, and you can see these overlapping orbitals, and finally Lin to however number, any number of million, and we're filling up this band, also known as the conductivity band here. Okay, so and it's this partially filled band, which is also known as I say, as a conduction band, which tells us whether or not our material is going to behave as a conductor, a semiconductor, or is going to be an insulator. Okay, so we know that electrons flow from high to low potential, and to do this, our metals, okay, have to have a partially filled valence band to be able to do that. Okay, so in our semiconductors and our insulators, they have a filled valence band, and they have a gap in energy between that and the conduction band above it. Okay. So the behavior that we see in terms of whether it can conduct electricity is dependent upon the size as the separation between the filled band and the gap of the next one. That's known as our band gap. So we came to this with the problem of why is it that some materials will act as a semiconductor if you ramp the temperature up. And the reason behind this is the fact that you're able to promote electrons to the higher energy state, so partially filling this band gap. And this is why things like silicone, okay, not silica, but silicone, can actually act as a semiconductor. Our insulators, such as diamond, for example, will have a large band gap. Okay, so this band theory explains why it is that some materials behave as a semiconductor and others don't. Okay, let's think about superconductors before I finish. Okay, so in 1911, a Dutch physicist, Heike Kamerlingh-Onnes, I probably said that terribly, so I do apologise, discovered that at very low temperatures, some metals have zero electrical resistance. This means electrical flow, but with zero loss of energy. The temperature at which this happens is actually known as the critical temperature. The highest being 23 Kelvin for niobium germanium alloy. And I used to use superconductors on a regular basis when I was looking at very weak sort of magnetic fields in sediments and rocks. And I used to use superconducting quantum interference devices, which were cooled by helium. It's also used in magnetic resonance imaging as well. Okay, not essential for you to know, but it's nice to know. So let's now think about how does a superconductor work. Okay, well, it was in the 1950s that John Barden and Leon Cooper and John Schrieffer suggested an explanation. Effectively, electrons like to work together. Okay, it's always better to work as a pair. Let us look at superconductors and think about shaping our life around them. Okay, it's a very simple explanation. Okay, so what happens is that you have this electron that starts to move through this lattice of atoms, and it does. Our negatively charged electron is slightly attracted to our positively charged nuclei. Okay, this distorts that lattice structure just a little bit, forming a little bit more of a positive region within that lattice. And then another electron is attracted towards that slightly positive region. So these electrons like to mosey on through together. It's a bit like following the cool kid at school. Basically, you have less resistance. The Cooper pair actually move through together. And so as they do this, they're less affected by the vibrations of those atoms within the lattice. So this is how a superconductor works. Another really cool thing that superconductors do is that they will repel a magnetic field when they're below that critical temperature, that critical point. They are so strongly diamagnetic they will actually repel. So it's actually been thought that this can be used. There have been some trials using this for kind of very fast bullet train type transport. It's known as the Meissner effect. And I just want to bring your attention to this. It was only 2 days ago, or no, 3 days ago actually, that some scientists at MIT discovered that a double layer of graphene, remember your casting mind back to the previous lecture about graphene, can actually behave as a superconductor. So if you have the 2 layers and you twist one layer relative to the other, it looks really pretty as well. It will actually start to behave, or it's thought to actually start to behave as a superconductor. But kind of like how cool, but it isn't that cool actually. It's an unconventional superconductor. So this is in our quest to find a superconductor that doesn't have to be cooled to the extent that they are, so make it usable and practical in everyday life. So if you, in your career, develop a superconductor that works at room temperature, I kind of want to be your friend, okay? Because whoever does that is going to be making a lot of money. So if you're interested in reading a little bit more about that, this paper was published. There were 2 papers published in Nature on the 5th of March, and it was called Correlated Insulator Behavior of Half Filling in a Magic Angle Superlattice. And the author was someone called Kao et al. Okay, well, et al means and others. Okay, so that's the end of the first lecture on solid and bonding structures. So as we know, our examples above are of crystalline materials. This means that we have atoms arranged in a repeatable pattern to form a lattice, and if you can predict that, that forms a long-range order. And we've looked at the different bonding types of our different bonding structures to relate that to the properties that they have. And just to finish off very briefly, we've kind of we haven't touched on this, but it's also important to mention quasicrystals. There was a fantastic poster presented a couple of weeks ago on quasicrystals. These are interesting. They have this Penrose tiled pattern, but one thing which is really important to note is they don't have a long range order. Okay, so in the next lecture, we'll basically be moving on to thinking about how we can determine crystal structure. So how we can analyze that little repeatable unit that we have in our crystals to actually determine their crystal structure. We'll also consider a little bit more about our ionic bonding as well. Okay.